So let's model or provide a simple model for static friction. Uh, the static friction is a force, and I'm going to give it the symbol lowercase f and put a little s, a little subscript s for static, and it is a vector. So we should give it units of, say, the Newton, and we have to describe the direction. So as a simple sort of situation to consider so that we can be motivated in order to kind of like accept the model that I'm going to show you, I have a mass on some level ground, and this is happening on the Earth, so there is an acceleration due to gravity in the background, and this massive object M has a weight, and that weight is equal to m times g. Okay, so static, what's meant by static is this object is stuck to the ground by some temporary weld or something like that. So in particular, what this static situation means is that these two surfaces are stuck to each other in the sense that they have no relative motion, but they are stuck that way as well. So I'm going to say that my object, M, has no acceleration. So that's what static means in this situation, no acceleration. And if it has no acceleration, by Newton's second law, that means that the net force on M adds up to 0. That's what Newton's second law says. Actually, Newton's first law as well. So let's think about what is the net force on M. Remember, I'm just motivating our model for static friction. So I know that in the net force on M, there is the weight force, this mg. It's an arrow down, so I'll draw the free body force diagram. So here is the little free body representing m, and there is a force down called the weight force, right? But because the net force is equal to 0 and I've got this mass and I think about it a little bit because I have my physics brain on, I note that the ground must be pushing upwards, supporting the mass, right? And that upwards force we've been calling the normal. Okay, so this is the normal force acting on M by the ground, and this is the weight force acting on M by the earth due to gravity, yada yada. But anyways, there it is. So this normal force is equal to the opposite of the weight force. And that's how the net force can be equal to 0. So since F net equals to 0, 0 equals n plus w, and this implies that the normal force is the opposite of the weight force. But you can also say that the normal force magnitude is equal to the weight force magnitude. They are in opposite directions. They are not Newton's third law pair forces, though. If please know that. Anyways, so let's think about what happens if I introduce another force into this problem. Let's set up a situation where there is a little person who grabs onto a rope and they pull towards the right on the mass M. And they can start pulling really weakly, and they can pull stronger and stronger and even stronger. So when that person turns on a pull force, oops, I should have completed this. This is W plus N. When this person turns on a pull force, they pull towards the right, and I'll just call it P, like this. If this object remains static, it must be because the ground can in some way pull back on the mass. So the ground pulls back on the mass with some sort of interesting force that I'm telling you to identify with friction. So that is the static friction force that shows up. If I pull harder, or if this little person pulls doubly hard, and the object still stays in static friction, that must mean that the static friction force also grew bigger. That is, the static friction force can take values from 0. We started with 0, and then all of a sudden we're up at something that is not 0 anymore. So the friction force is growing as you pull harder and harder on the object. But at some point, you might be able to pull with a force that the friction force can't match. And in that case, the friction force cannot be big enough to cancel or balance against the pull force. And the net force is no longer 0. And that means, therefore, the acceleration is no longer 0. And this object breaks free of the static situation. And so what we say is that there must be a maximum value of the static friction force. And the way this gets modeled, this maximum value, the way it gets modeled is it is proportional to how tightly stuck, or how hard this mass is being pressed down into the surface. You can imagine that if this mass was heavier, you would have to pull harder, probably. So if the mass is twice as heavy, this model says that the maximum available static friction force will have to be twice as much. That constant of proportionality in this model is given a symbol. It's called mu sub s. So it's mu sub s times n, where n is the magnitude of the normal force. Notice that I haven't drawn any vector arrows because it's not appropriate right now. The static friction force is going to be along the plane, but the normal force is up down, right? So I can't draw an equal sign between two arrows that don't point in the same direction, for example. Mu sub s is just a number. Mu sub s is a number that's bigger than 0, and it has no units. Oh, that's not true. Mu sub s, no, that is true. No units. Okay, so you notice there's this equal sign. I'm going to make this really confusing. I'm going to go down and I'm going to draw this. I am not going to put the word max. I'm going to say that friction is going to be smaller than or equal to mu sub s n. So the smaller than cases were the cases that I was exploring earlier on. But then at some point, the pull force is above the equal sign, and it's above the maximum available friction, static friction force. And so you can cause the mass to slip and start to slide. So this is the simple model for static friction. I want to note really quickly about the direction of the static friction force. And the best I can come up with to describe how to do it, or how to understand the direction, is opposite of all the other influences added together. Yeah, it's just in the other direction. So you see this friction force here, I drew it to oppose the pulling force. If I had a few people pulling at different directions, say along the level ground, then the static friction force would just have to add up to be the opposite of the summation of all those pulling forces on the other side. Okay. So the next model is for kinetic friction. And the truth is this one is simpler. So put a little k, and it is a force, and we'll still use the lowercase f. Yeah, so Newton's deserves a direction. So let's model kinetic friction. So kinetic friction is way easier, and it simply gets written this way. The kinetic friction force is going to have a magnitude equal to some coefficient called mu sub k multiplying times the magnitude of the normal force. This is it. And this is our simple model. It is that simple. All right, so I'll just make a note. Mu sub k is also bigger than 0. But when you go and you compare to the static case, there are reasons to suspect that in these models, mu sub s needs to be bigger than mu sub k. Mu sub k also has no units, right? Newtons times something without units is newtons. That's the only way that works out. But mu sub s is bigger than mu sub k. The idea is, I don't know if you've ever noticed, but anytime you try to cause something to slide, you have to add force, and then there is a point at which the thing breaks free. And that breaking free is a situation of going from static to kinetic is kind of violent. It's like it pops free, and that's the origin of the static being bigger than mu sub k. I'm not explaining that very well, but that's the idea. Direction-wise, this is interesting. The friction force has a direction that is opposite to the relative motion. So if I imagine here is a box that's moving this way. Let's say the box has a velocity, so this is a velocity vector, not a force vector. If it's moving that way, then there is a friction force, right? And it's going to be kinetic because you see the motion over the ground. The friction force is going to be back to the left, like that. So it's always opposite to the relative motion of the surfaces. Okay, so that's the simple model for kinetic friction. The problems become pretty tough when you study friction on inclined planes. The normal force is not in the vertical direction, and the friction depends on in which direction is this object moving. So an interesting case is, what if this object is actually moving up the plane like this? Then the friction force is going to be opposing like this, but also on this object is a weight force vector. And these are the three forces that dictate the acceleration of that object. Okay, thanks.